Good morning.
Good morning, sir.
Good morning. Are you there?
Morning, sir.
So you should respond. Just wait. Okay. Now can you say where we left in chapter 8? Have I worked out this example 8.9? Example 8.9, have you worked it out or not? This one? Okay. Okay. Okay, then these are the assignment exercises, these three, and I have to write another one. Just wait, probably 8.47, I think. Yes, 8.47. So the last one will be 8.47. A 0.150 kg glider is moving to the right on a frictionless horizontal air track with a speed of 0.80 meter per second. It has a head-on collision with a 0. Who is there? 0.300 kg glider that is moving to the left with a speed of 2.20 meter per second. Find the final velocity, magnitude and direction of each glider if the collision is elastic. If the collision is elastic. Okay. So this is the last assignment exercise. So take a screenshot. Then have you taken the screenshot of this question? Have you taken the screenshot of this question?
Yes, sir.
Okay. Okay, then we have to go for the two test your understanding 8.2 and 8.3. What are they? Just wait. Test your understanding. 8.2 and 8.3. So what are they? Just let me see. 8.2. Okay. A spring, a spring loaded, a spring loaded toy sits at rest on a horizontal horizontal frictionless frictionless surface. When the spring releases, when the spring releases, the toy breaks into three equal mass pieces. Equal mass pieces A, B, and C, which slide along the surface piece A moves off in the negative x direction, x direction while piece B moves off in the negative y direction. A. What are the SIG signs of the velocity components velocity components of piece C, and the other bit is which of the three pieces is moving the fastest. Fastest. Okay, this is then PYU 8.3 for each situation. Okay, so 8.3 we should not write, I will just discuss. Okay, now you see this is test your understanding 8.2. A spring-loaded toy sits at rest on a horizontal frictionless surface. When the spring releases, the toy breaks into three equal mass pieces A, B, and C, which slide along the surface. Piece A moves up in the negative x direction, while piece B moves up in the negative y direction. What are the signs of the velocity components of piece C? Which of the three pieces is moving the fastest? Now you see, because you will be answering MCQ type questions, so you need not do much of theory. You should estimate and try to do all these type of questions. So let us discuss about these questions. Okay. Yes. Anybody? Asutosh.
Chapter 8 is not started yet, sir.
Asutosh, what happened? Asutosh, what happened? Asutosh, you were telling something. What happened? Chapter 8 is not started. Who told you chapter 8 is not started? Hello? Asutosh, what are you doing? Oh, we have not started. Then what we are doing in the last 3 classes?
Sir, energy flow diagram.
Huh? Oh, energy diagrams. Okay. Okay then. Okay. So I will be starting chapter 8. Okay then. Okay. So you see, um, okay, just wait. So you are able to see my screen?
Yes, sir.
Okay. So,
Yes, sir.
okay. Now, if I have not started chapter 8, then who told you when I asked you whether this example has been done or not? Somebody told yes. So, chapter 8. Okay. Now you see there is a new concept in this chapter. There are 2 new concepts. One is momentum and the other is impulse. So first I will discuss on momentum. Okay, very elementary idea because now no derivations will be asked, only MCQ type of question. So we should go in a hurry. Momentum is designated or denoted by the symbol P, small p. It is a vector quantity. It is the product of a scalar mass m and a vector v. So this is momentum. Its SI unit is kg into meter per second. So kg into meter per second. Okay. So this is momentum. Okay, you can express why I am defining momentum, because I can express Newton's second law in terms of momentum. What is Newton's second law? The net force F acting on a body can be expressed as the rate of change of momentum. So this is how force is quantitatively defined. So this is a very fundamental law of Newton's. Its status is much higher than the first and the third law because it gives you a quantitative definition of force. Okay, so this is Newton's second law of motion in terms of momentum. Are you able to understand? So first I defined momentum, then I expressed Newton's second law in terms of momentum. Then I defined another new concept which is called impulse. Now what is impulse? Impulse is change in momentum. Okay, this impulse, sorry, first I will define impulse, then I will express the impulse momentum theorem. Impulse J is defined as net force into time interval. So net force into time interval when the force is constant. Remember, when force is constant, when delta F is constant, when sum of F is constant. When force is constant, you can write delta F by delta T as dp. This is constant. Okay. So when force is constant, you can write dp by dt is also equal to delta p by delta t. That is possible. Okay. So if I will use this in place of this delta f, if I will write delta p by delta t, then delta t cancel, and you will get J is equal to delta p, which is impulse momentum theorem, which we will discuss later on. So I should not write it now. Okay, so I have defined the impulse for a constant force. When the force is variable, the same impulse can be defined as J is equal to integral T1 to T2, integral T1 to T2 net F, that is the force, okay, and dt. So this is the impulse, and its unit is same kg meter per second or Newton second. Either it will be Newton second or kg meter per second, same thing. Okay, kg meter per second. Okay, then impulse momentum theorem. Impulse momentum theorem. If you have remembered work energy theorem, you see there is force, there is displacement, there is work, and there is kinetic energy, isn't it? So in impulse momentum theorem also, you have got force, in place of displacement you have got time interval, and in place of work you have got momentum. So what is work energy equivalence principle? When a force A does W amount of work by displacing a body through a displacement ds, then the work done, whether the force is constant or variable, we can write it as FDS integration. You see, let us take a variable for FDS or FDX x1 to x2. Okay, this is how I defined my, so this ds become x actually. uh, so fdx, this is also fdx, and this is equal to change in kinetic energy delta k. Similarly, in impulse momentum theorem, you have got force, you have got impulse, all are vector quantities. This is also vector quantity. Here this is vector quantity, okay, and this j is a and you have got displacement, sorry, interval of time dt, and then change in momentum p, as there is change in this is delta p, isn't it? So you can write it as j is equal to this impulse is equal to integration. um, you have to find out uh, integration T1 to T2, T1 to T2, net force, okay, then dt. Here also that is the net force. This F is also net force, and that is equal to delta P, change in momentum. Okay. So impulse is nothing but change in momentum, as work is nothing but change in kinetic energy. So we learned about momentum, we learned about Newton's second law in terms of momentum, we learned about impulse, and we also learned about impulse momentum theorem. Now, why we have learned all these things? The main thing is that momentum is very fundamental like energy. As energy is conserved, similarly momentum is also conserved. What does that mean? So let us discuss about that thing. So suppose there is a, I am just giving an example so that you can appreciate it. Suppose there is a room which is closed, or closed means isolated. That doesn't imply it doesn't have door, it doesn't have window. It has door, it has window, but everything is closed. So there is no contact or no connection between the outside environment. And I have kept two persons inside the room with food and all amenities of existence. That means they can lead a life. And I gave each of them 50 rupees, 50 and 50. So what is the total amount of money? If I add them, 50 plus 50 is equal to 100. But there is all possibility of changes in their amount. Suppose this fellow is sleeping, then this fellow can take 20 rupees from his pocket. So what will happen? Initially they have 50 plus 50, then this 50 plus 50 is 100, If one person will take 20 rupees from his friend, then this will become 30 plus 70. If the other person will take all the 50 rupees, then this can be 0 plus, this can also be 100 plus 0. All kinds of possibilities are there. But always, whenever you will add them, you can never get less than 100 or more than 100. That means the sum individually there is changes, but the sum always remains constant. For whom? For a isolated system. Similarly, for an isolated system, system means either bodies or particles more than one. Okay, so if the initial momentum of the first particle is p1, and if the initial momentum, so how in this book, how the notations are written, actually these notations are written in three symbols. If the body is A, the name of the body first, initial or final, that is either in 1 or 2, then the component PA1X. Okay, that means suppose because momentum is a vector quantity, it has three components. So if P is conserved, then that implies that the X component is also conserved and the Y component is also conserved. If there are two bodies only, then I can write my equation as PA1X. What does that mean? That means X component or initial X component of body A plus initial X component of body B is equal to final X component. I will write it as final X component of body A plus final X component of body B. Final X component of body B. Similarly, I can write for Y component and Z component, isn't it? So, for an isolated system, your total momentum is a constant quantity or a conserved quantity. So, P is equal to constant. That you can derive also, because for an isolated system, your net force acting on the system is 0. Okay, so you can start with that and you can end with P is equal to constant. So how I should write? Because the system is isolated or closed or no connection with the environment, so net force is equal to 0. But according to Newton's second law in terms of momentum, my net force can be expressed as rate of change of momentum is equal to 0. So dp by dt is equal to 0. Whose time derivative is 0? A constant, because a constant does not change with time. So I can write dp by dt can also be written as d by dt of a constant quantity, constant c. So this gives me P is equal to C or P is equal to constant. This is how I can derive my conservation of momentum, which is a very fundamental principle. Now, where I am going to apply this conservation of momentum? Conservation of momentum can be applied in collision. What is a collision? Collision at least involves two particles or two bodies. Normally, collisions are inelastic in nature. What is inelastic collision? The total initial kinetic energy is not equal to total final kinetic energy. The total final kinetic energy is always less than the total initial kinetic energy. How do you know that? Because when I drop a ball from a height to the floor, the ball collides with the floor and doesn't rise to the height from which it was thrown or it was dropped. Rather, it will rise a height less than that, because some amount of energy is lost in the form of sound. That's why when the ball touches the floor, I hear a sound. But in certain special situations, the collision can be elastic. In elastic collision, the total kinetic energy before collision and after collision are same or remain same. In nature, you will not find elastic collision frequently. but you all collisions are inelastic in nature. In inelastic collision or elastic collision, momentum conservation is a must. Momentum conservation is obeyed both by inelastic collision and elastic collision. But in addition to the momentum conservation, elastic collision obeys conservation of kinetic energy also. So when I say elastic collision, you must understand that there are two conservation laws which are applied elastic collision. What are they? The total elastic, the total P is a constant. The total P is equal to constant, that is 1. P is equal to constant. Okay. And K is also constant. The total kinetic energy is also constant. Before collision, the total P, and after collision, the total P are same. Similarly, before collision, total kinetic energy, and after collision, total kinetic energy are same. But if the collision is inelastic in nature, inelastic, inelastic, if the collision is inelastic in nature, then P is constant. That is a must. That is very fundamental. Okay, but your K is not constant. Normally what happened? K2 is bigger than K1. K2 is less than K1. Actually, some amount of energy is dissipated or lost in inelastic collision. We will work out examples and we can see that. Okay, so this is all about chapter 8. So can anybody summarize what I told you about on chapter 8? Yes? Can anybody say? Don't keep quiet. What have I told you? Anjali Priya. Anjali Priya, are you there?
Yes, sir.
What are the 4 or 5 things that we learned in this chapter? Tell me in sequence. You were not there. Are you present throughout the
Sir, I was
class?
absent from the last two classes.
Huh?
Sir, I
What
was
happened?
absent from the last two classes.
What happened? Second. Then there is impulse momentum theorem. Impulse momentum theorem says that the total impulse is equal to nothing but change in momentum. Okay. Then why we are after momentum? Because momentum is a conserved quantity. Okay. The sum total of momentum for an isolated system remains constant. The initial momentum of the system is equal to final momentum of the system if the system is isolated, or the net forces acting on the system is 0. When I mean system, it must consist of more than one particle. So one particle's momentum may not be constant, but the system's momentum is always constant. That you must understand. And why once we learn conservation of momentum, then we will apply it. We will apply in the case of collision, because collision involves at least two particles. There are two types of collision. Normally, the generally collision is inelastic in nature. That means its final kinetic energy of the system will be lower than the initial kinetic energy, because some energy has to be lost to the environment. But in elastic collision is a special type of collision where the kinetic energy initially, that is before collision, and after collision of the system is same. Okay. So this is how we have learned all the physics in chapter 8. Then we will do examples. We will do two examples. 8.4 first. A marksman holds a rifle of mass MR is equal to 3 kg loosely, so it can recoil freely. He fires a bullet of mass 5 gram horizontally with a velocity relative to the ground, that is VBX is equal to 300 meter per second. What is the recoil velocity of the rifle, and what are the final momentum and kinetic energy of the bullet and rifle? Okay, so how I am going to do this problem? So this is a system which consists of two things. What are those two things? Yes, what are those two things? Just
Rifle
remaining.
and bullet.
Yes,
Rifle and bullet.
rifle and bullet. Good, very good. You should respond. Okay, so the system is rifle and bullet. Okay, then which concept of physics I will apply to this problem? Yes,
Conservation of momentum.
conservation of momentum. That means the conservation before collision, BP before collision, that is initial P1 is equal to P2. What is P1? This capital P1, can anybody say? This is the sum of the momentum of the rifle and the bullet. But because the rifle and the bullet are moving horizontally, so your problem, your life is very simple. What you will do, there is no vector, only the x component is involved. So you can write P1x is equal to P2x. That means all x components of the momentum before collision and all x component of the momentum after collision are same. Okay, so P1x now consists of two quantities. What are those two quantities? One is the initial momentum of the rifle. So I will write rifle for R, then initial for 1, x for x component, plus the initial x component of bullet, that is P bullet, 1 for initial and x for component, that must be equal to initial moment, sorry, final momentum of rifle. Final means 2, rifle means R, x component means x, plus final x component of bullet, B for bullet, 2 for final, x for component. So you see I am using three notations. Okay, now everything is, now 99% of your problem is over if you are capable of writing this equation. Now you have to put the value. What is the before collision? What is the speed of the gun? Yes, what is the speed of the gun before collision? Yes,
0.
0.
0. And what is the speed of the bullet?
0.
0. 0. So PR1x is equal to 0 and PB1x is also 0. So you get the left hand side is equal to 0, and that is equal to two quantities PR2x plus PB2x. Okay, now we'll write in place of PR2x, what should I write? So let us write it. So I will write VR2x, isn't it? I will write MR, mass of the rifle, into final velocity of the rifle's x component. Similarly, plus mass of the bullet, because that is what is the definition of momentum, into velocity, final velocity of the bullets in x direction or horizontally. Okay, now you can take it to one side because you want to find out VR2x. Okay, so you can take this, because this equal to 0, so MRVR2x is equal to minus is equal to, just wait, is equal to minus this much. Okay, so Vr2x, Vr2x is equal to minus mb divided by mr, mass of the bullet, by mass of the rifle into velocity of the final velocity of the bullet horizontally. Now you have to put your working formula is ready. Now you have to put only values. What are the values? Yes, tell me. What are the values? You have to put a equality, then minus 5 gram. You have to express it in kg. So 5 into 10 to the power minus 3. That becomes kg. And what is the mass of the gun? It is 3 kg. And what is the velocity of the bullet? 300 meter per second. So I will write 300 as 3 into 10 to the power 2. So and then I will do the calculation. The calculation is 3 cancel, 10 to the power minus 3 into 10 to the power 2 is power 10 to the power minus 1. So that will be minus 5 by 10 is equal to minus 0.5. 0.5 and unit is meter per second. So this is the speed of the gun and the direction is opposite to the direction of the bullet. That means if the bullet goes in this direction, the gun will goes in this direction. This is what is called recoil velocity of the gun. So that's why you have to carry the gun loosely. Otherwise the impact on your shoulder will be so high that there will be injury to your shoulder. Okay, so you must have a gap between the gun and your shoulder, so that once the bullet is fired, there is space for the gun to go backward. So it will not. So don't. So normally they don't hold the gun very tightly to their shoulder. That is what the problem is also telling you. A marksman holds a rifle of mass 3 kg loosely. Okay, so I think how powerful this conservation of momentum technique is there. But we are halfway. We have to find out the initial moment, the momentum of the bullet and the gun. Okay, what is the final momentum of the bullet? Final momentum of the bullet is mass of the bullet into velocity of the bullet. So what is the mass of the bullet? Mass of the bullet is, so I can write it as, just wait, I can write PB2x. That is final momentum of the bullet is equal to mass of the bullet 5 gram is 5 into 10 to the power minus 3 into its velocity, which is 3 into 10 to the power 2. 3 into 10 to the power 2, and the unit is kg meter per second. Kg meter per second. Okay, so from here you will get 3 into 5 is 15, so 1.5 kg meter per second. The this is positive, that means the momentum is directed along the positive x-axis. Now can you say what will be the final momentum of the gun without calculation? Can anybody say what will be the final momentum of the rifle? Yes,
Same 1.5 kg meter per
minus
second.
1.5, minus 1.5, because
Okay,
you
okay.
see
Sorry.
this PR2x plus PB2x, their sum must be 0, because the total initial momentum of the system was 0. So 1.5 should be added with what, so that it will produce 0? It must be added with minus 1.5. So it will be minus, that is, it is in the negative x-axis, and that is what actually happening. If you do the calculation also, you will get the same minus 1.5, because now you have to use in place of velocity minus 0.5, and the mass of the rifle is 3. So 3 into 0.5 is 1.5. There is a minus, so minus 1.5. And you have to find the kinetic energy of the bullet and the gun also. Final kinetic energy. So what is the final kinetic energy of the bullet? Half mv square. So half into 5 into 10 to the power minus 3 into 300 square. 300 square is 3 into 10 to the power square is 3 square is 9, and 10 to the power 2 square is 10 to the power 4, isn't it? So what do you get? So minus 3 plus 4 is 110. So 2.5 into 9 is 22.5 into 10 is 2225 joule. So the kinetic energy of the bullet is 225 joule. So very heavy kinetic energy. Can you say why the bullet has so much kinetic energy, though its mass is only 5 gram? Why it has so much kinetic energy? Because its velocity is very high, and kinetic energy is directly proportional to the square of the velocity. That is very important. But you see, the the rifle's velocity is only 0.5, isn't it? The speed is 0.5 and its speed is 300. So 600 times more speed, isn't it? But the mass is 5 gram and the other mass is 3000 kg. So how many times it is more? Can anybody say? How many? You see, the mass of your bullet is 5 gram and mass of your rifle is 3000 gram. 3 kg means 3000 gram. So how much heavier the mass, the rifle compared to the gun? Yes?
600.
600 times. You see, 600 times. So because the expression for a kinetic energy, this is actually very enjoyable. I don't use formula. That's why I do physics in this way. You see, kinetic energy is equal to half mv square. What does it mean? Your kinetic energy is directly proportional to mass. So because the mass of the rifle is 600 times more than the mass of the bullet, so the rifle must possess 600 times more kinetic energy. But this part is there. Second part is, your kinetic energy is directly proportional to the square of the velocity. So what is the velocity of the bullet? It is 300 kilometer per second. 300 meter. 300 meter per second. This is its speed. And what is the speed of the gun? It is half meter per second. Sorry, I should write 300 meter here. So 300 meter per second here and half meter per second here. Just wait. So this is half meter per second. So the speed of the bullet is how much times more than the speed of the gun? Yes? Yes, how many times? The speed of the bullet is how many times? 600 times, because 300 divided by half will be 600. So now you see, your mass is 600, mass of the gun is 600 times more than the mass of the bullet. So the kinetic energy of the gun should be 600 times more than the kinetic energy of the bullet. But that is not the whole story. The second part of the story tells you that kinetic energy is directly proportional to the square of the speed, and the speed of the bullet is 600 times more than the speed of the gun. So how much more kinetic energy? 600 square. So 600 square means 3600 times more kinetic energy the bullet will have compared to the gun. But already the gun has 600 times it has achieved in comparison to the mass. So 3600 divided by 600, finally the bullet's kinetic energy must be 600 times more than the kinetic energy of the bullet. Okay, the kinetic energy of the bullet must be 600 times more than the kinetic energy of the gun. So if I will divide by 600 to this 225, then I will get the kinetic energy. This calculation one can do very quickly in his mind, very quickly. So 20 means 2.25. So this 20 is cancelled. Then finally you will get energy 6 divided 2.25 divided by 6 will be 6 18 4.40 6 7 42 0.375 joule. If you do the calculation, you will also get the same thing. But I will not do the calculation in this way. Rather, I will do the calculation in this way, and my mind will process the whole informations within 10 to 15 seconds very quickly. Once you make it a habit, then the processing speed will be very high. Just for sake of comparison, I am just telling you how we will be getting the same thing. So what will be the kinetic energy of the gun? Half mv square. In place of m I will put 3, and in place of v half square. Half square is 1 by 4. So you will get 3 by 8, and 3 by 8 is nothing but it is 0.375. So this is also 0.375. So this is how you will see the kinetic energy of the rifle, the kinetic energy of the bullet, the momentum, final momentum of the bullet, final momentum of the rifle. Okay. Now we'll go to the second part of the example. A 1000 kg car traveling north at 15 meters per second collides with a 2000 kg truck traveling east at 10 meters per second. The occupants wearing seat belts are uninjured, but the two vehicles move away from the impact point as one. The insurance adjuster asks you to find the velocity of the wreckage just after impact. What is your answer? Okay. Why this always takes a lot of time in clearance? I don't know why. Okay. So you see your car is traveling north. So you have got a vertical component of the momentum. And your torque is moving in east, so you also have got a horizontal component of the momentum. So now you have got x component of the momentum and y component of the momentum. So now your conservation equation will have two parts, an x component part and a y component part. Why it is taking so much time in clearance? Yes. It is. Unnecessarily, it is taking so much time. Hello, are you able to see my screen?
No, sir.
Now?
Yes, sir.
Okay. Now you see your car is moving in the north direction. Truck is moving in the east direction. And there is a collision. So we have got two components. So our system has C means car, and T means truck. And east means X component, and north means Y component. Okay. Now I will use my conservation equations. You tell me, how should I write? Yes, tell me. Initial momentum of the car along X plus initial momentum of truck along X is equal to final momentum of car along X plus final momentum of torque along x. Okay, this is one part of the equation. The second part of the equation, I will just use y. I will change into y. That I will do later on. Just wait. So this is my car and this is my torque. So what should I write? PC1x. Tell me, what is the momentum? It is the mass of the car into velocity of the car along x component. Velocity of the car along is x component. Okay. Similarly, mass of the torque, okay, and velocity of the torque in along x, that is equal to, now both of them after collision move as a same unit, so the velocity is same, only mass will be different after collision. So mc v, I will write it as v2x. So there is no question of car and torque now, because both of them are moving with the same velocity, and mass of torque into velocity v2x. Now tell me, your car is moving along the north direction. So what is its x component? It is a vector which is along the y-axis. What is its x component? Yes? 0. So this part is 0. Okay. What is the mass of the torque? Mass of the torque is 2000 or 3000. Let us see. The 2000, and it is moving with 10 meter per second. I just wait. So 2000 into 10, because it is moving with 10 meter per second. Okay, is equal to, if I will take v2x as common, then inside the bracket I will have mc plus mt. 1000 plus 2000 is 3000. So I will have 3000, isn't it? And its speed is 20,000, isn't it? What is its speed? So 2000 kg torque traveling is at 10 meter per second. Okay. So so you will get this 20,000 by 3000. 20,000 by 3000 will be your v2x. 3000 is equal to v2x, meter per second, of course, naturally. Okay. So 0, 0, 0, 0, 0, 0, 20 by 3. So I get my v2x as 20 by 3. v2x is equal to 20 by 3 meter per second. Okay, 20 by 3 meter per second. Then I will apply my y component. So in place of x, I will write y. This all will be replaced by y. Okay, so I will get another conservation equation. So I will write y here, y here, y here, and y here. Again they are moving. So now you see the torque. What will be the torque's y component? It will be 0, because the torque is moving along the x-axis. So this part will be 0. All this will be y again. This will be y, but this is not going to be 0. That you must understand. Okay, this is not going to be 0. And this x are replaced by y. Okay, so I will represent it by y. This is also y. This is also y, v2y. Okay, same v2y. Okay, here also this is y. This is y. Okay, so this is 1000 into 15. This is 15, isn't it? This part is 0. So now you have got 15,000 in place of 20,000. You have got 15,000. This is 1, 5. 15,000 by 3,000 will be 5. So your v2y is equal to V2y is equal to 5 meter per second. 5 meter per second. Okay, so that I have calculated probably here. You see, I have got 20 by 3 meter per second my V2x, 5 meter per second my V2y. So what will be my magnitude? V2x square plus V2y square, which I get as 625 by 9. Okay, because 20 by 3 square will be 400 by 9 and 5 square will be 25. So 25 into 9 will be 225. 400 plus 225 will be 625 by 9. Square root will be 25 by 3. That is 8.31 meter per second. And what will be the angle? Tan theta is equal to V2 by V2x, which is 0.75. So theta is equal to 37 degree. So the question was telling you, what was the question actually telling? What is your the occupants? The insurance adjuster asks you to find the velocity of the wreckage just after impact. So you will say that the velocity of the wreckage, that means both of them will move with a speed of 8.31 meter per second, making an angle of 37 degree with the horizontal. So that will be your answer. And I think you should take a screenshot of these questions. You just take a screenshot. Have you taken the screenshot? So you take a screenshot of, I have already worked out 2 examples for you. You take a screenshot of these assignment exercises. These are 3. Then I will give you another 1. Have you taken a screenshot?
Yes, sir.
Yes. Then you take another screenshot of this one. With the test your understanding 8.2. 8.2 I will discuss in the next class. 8.3 also I will discuss in the next class. And then we will start chapter 9. So you say 8.47, test your understanding 8.2. That you also take a screenshot. Have you taken? Yes. Have you taken?
Yes, sir. Yes, sir.
Okay. Okay. So thank you for your attention, and we will be meeting in the next class. So with these words, I am stopping here, and thank you very much, and have a nice day. Okay.
Thank you, sir.
Good afternoon, all.
Good afternoon, ma'am.
What we have
Good
discussed in the
afternoon, ma'am.
last. Good afternoon. What we have discussed in the last class? Yes.
मैम वो जो मैंने बोली थी ना वो जो नहीं हो रहा है वो गूगल ये ना वो नहीं हो रहा है